Hi, welcome back to Math 111. We are going to round out Chapter 3 today by discussing complex zeros and something called the fundamental theorem of algebra, along with a couple of other theorems. Sorry. All right, so let's start with this. So let's think about for a minute the polynomial p of x equals x squared plus 1. We know from previous conversations that if we sketch the graph of this thing, it looks like this, right? So it has no real zeros. Makes sense, because if we try to solve this algebraically, we get to x squared equals -1. We know this is not a real number. We know that anytime we square a real number, we're going to get a positive number. Remember, though, that there's a whole nother class of numbers called imaginary numbers. And those are based on this thing called the imaginary unit, which says that, okay, fine, we know that the square root of -1 does not exist in the real world. But let's pretend it does, and let's call it an imaginary number. And just because we can't see it doesn't mean it doesn't exist. So we're going to say that if x squared equals -1, we're going to go ahead and take the positive and negative square roots of both sides of this equation and get a number that is the square root of -1. We're going to call that number I. Now, this can be kind of hard for us to wrap our brains around because we live in the visible world. But imaginary numbers, this imaginary unit is, yes, it's imaginary in that it's not a number we can put on the number line. It's not a counting number. However, this thing has very significant, important ramifications in the sciences. There are physics that we can observe that cannot be explained without I. There are behaviors of electronics that we can observe that cannot be explained without I. So, yes, it is imaginary in that it doesn't exist in the real physical plane, but it is an important concept, and so we accept that the square root of -1 is equal to I. This is one of the things you need to be able to internalize and understand, this basic fact. When you see I, you need to think square root -1. Okay, some things about this imaginary unit I. Because I is defined as the square root of -1, if we square I, we get -1. So I squared equals -1. We can also use I to simplify the square roots of negative numbers. So if we take the square root of some negative real number, we will get I, because that's the square root of -1, times the square root of that number. So, for example, the square root of -4 is I times the square root of 2, or square root of 4, which is 2. We usually write that just as 2I. The square root of -3 is I times the square root of 3. We put the I in front of the square root just to avoid any confusion. This sometimes trips people up. Complex numbers will be some real part plus some imaginary part. This 3 plus 2I is a complex number. 7 minus 1/2 I is a complex number. 3 is a complex number, because you could write 3 as 3 plus 0I. So what I'm trying to demonstrate here is that all real numbers are complex, with the imaginary part simply being 0I. This is something to understand and accept, because when we start talking about finding all complex roots, that means real and imaginary. Okay, so let's do some real quick reminders of how we operate with complex numbers. Essentially, we add real to real and imaginary to imaginary. So to simplify number 1, we would just take 1 minus 2i, distribute the negative sign through the second one, and we would get negative 2 minus 6i. Okay? To do this type of multiplication for number 2, we FOIL. So first is 1 times 3, and then outer is plus 1 times 4i, and then inner is minus 3 times 2i, and then last would be minus 2i times 4i. All right, so 1 times 3 is 3. 4i minus 6i is minus 2i. Now, this one's a little tricky because we've got is negative 2i times 4i. Well, 2 times 4 is 8. I times I is I squared, which is negative 1. So we end up with 3 minus 2i minus negative 8, which means plus 8. So 11 minus 2i is what this simplifies to. Okay. Let's go through this number 3 because division can be a little tricky. So 1 minus 2i divided by 3 minus 4i. This is how we do division with imaginary numbers. Now, this textbook, let's see, how do they? Yeah, so there's a thing called a conjugate. What we're going to do is we're going to do something called rationalizing the denominator because I is a radical. So how do we handle that when we were rationalizing radicals? Well, we added the conjugate. Sorry, we didn't add the conjugate. We multiplied by the conjugate on the top and on the bottom. Foil that top out, we get 3 minus 6i minus 8i minus 8 times, so minus 2i times 4i all over, so 3 minus 4i multiplied by 3 plus 4i. My top is going to simplify. This is going to become plus 8, so I'm going to have 11 minus 14i. No, I screwed something up. What did I screw up? 3. Oh, this should be plus 4i. Sorry. So this should be, not that. There we go. Minus 2i. There we go. All over. Now here's the deal. We recognize this as a difference multiplied by a sum. Remember, if we FOIL that out, we're going to get 3 squared minus 4i squared, which is 9. 4i squared is negative 16 plus 16. So this is 11 over 25 minus 2 over 25i. The trick here is to remember when we rationalize a radical, we multiply by the conjugate of the denominator. Okay. Number 4 and 5 look very similar, but they're actually different, and here's why. Remember, in our order of operations, we simplify first. So that means that we take the square root of negative 3, and we write that as I times the square root of 3. And then we take the square root of negative 12, and we simplify that down to I times the square root of 12. Now, when we multiply those together, we get I squared times the square root of 36. We know I squared is negative 1. We know the square root of 36 is negative 6. So this is the square root, this is negative 6. For 12, because they're under a single radical, negative 3 times negative 12 is 36. The square root of 36 is 6. So be very careful with these two. They are different. All right, and this last one looks ugly, but it really isn't too bad. We just FOIL. X times x is x squared. Outer times outer is minus x times 1 minus 2i. Inner times inner, same thing, almost, minus x times 1 plus 2i. And last times last is going to give me a plus 1 plus 2i times 1 minus 2i. Now we'll distribute where we can. So we've got x squared minus x plus 2xi minus x minus 2xi plus 1 plus 2i minus 2i minus 2i squared. Those go away. Those go away. And what we're left with is x squared minus 2x. This is plus 1. This is minus 4, so plus 1 minus a minus 4 is going to be plus 5. So what we're showing here is that we know that this polynomial will not factor with real factors, but here we were able to factor it with imaginary coefficients. What this means is that 1 plus 2i is a 0 of this polynomial, and 1 minus 2i is a 0 of that polynomial. These are both complex zeros of a polynomial that we know would actually not have any real zeros because they're complex. Okay, notice 1 plus 2i, 1 minus 2i. Those are conjugate pairs, just like we talked about conjugate pairs when we were doing radicals. We're going to talk about conjugate pairs in relation to imaginary numbers. So if we've got a complex number, a plus bi, the conjugate of that number is a minus bi. This textbook uses an overbar to indicate conjugate. So a plus bi, this with an overbar, means the conjugate of a plus bi, and that's going to be a minus bi. And here are some examples. Notice we can talk about the conjugate of 6, and that's just 6. Because 6 is 6 plus 0i. So its conjugate would be 6 minus 0i, which would still just be 6. Do not get confused with something like 4i. That is 0 plus 4i. The conjugate of that is 0 minus 4i. Now, when we start introducing complex numbers, we have to be really careful with the term conjugate, because conjugate, as we use it in terms of radicals, can get confusing. So we are going to realize that when we use this overbar, we are only going to change the sign on the imaginary part. So 3 plus square root 5, that's all real. The imaginary part is implied. If we want to take the conjugate of that, that's all real. Change the sign on just the imaginary part. And we still get 3 plus 5 square root, or square root 5. Okay, so why do we care? Well, here's why we care. We talked about this a minute ago. We find the zeros of this polynomial using the quadratic formula, And we get 1 plus or minus 2i. Couple of things to note. The zeros, 1 plus 2i and 1 minus 2i, are complex conjugates. Imaginary numbers, actually complex roots, complex zeros, will always come in conjugate pairs. So if 1 plus 2i is a root, you know that 1 minus 2i is a root. We've already shown that we can multiply these two factors together and get x squared and get the polynomial we started with. All right, so we're going to put all of this together and realize that what this means is that we now know exactly how many roots a polynomial will have. A polynomial of degree n will have exactly n complex roots or complex zeros. So a fifth degree polynomial will have 5 zeros. Some of those may be real. Some of them may be rational. Some of them may be irrational, and some of them may be imaginary or have imaginary parts. So we can put all of this together. Let's practice. Let's find all the complex zeros of this polynomial and state their multiplicity. So our polynomial is (12x to the 5th minus 20x to the 4th plus 19x to the 3rd minus 6x squared minus 2x plus 1. Here's what we know. We know that this thing will have 5 complex zeros. Some of them might be real, some of them might be rational, some of them might be repeated. So what do we know? Well, we know we've got 1, 2, 3, 4. So we've got 4, 2, or 0 positive real roots. Let's take a look at f of negative x. It's going to be negative 12x to the 5th minus 20x to the 4th minus 19x to the 3rd minus 6x squared plus 2x plus 1. 1, 2, 3, 4. So we have exactly 1 negative real root. Let's look at our possible rational roots. So P's are the coefficients of the constant terms, such as positive or negative 1. Q are the coefficients of, factors of the leading coefficient. So it's going to be positive and negative 1, 2, 3, 4, 6, and 12. So my possible rational roots are P over Q, which is 1, 1/2, 1/3, 1/4, 1/6, and 1/12. All right, I'm going to hope against hope that life is simple, and we're going to try negative 1 first. So let's do synthetic division with -1. Drop down the 12. This is not looking promising. Not promising at all. Okay, so -12 is not looking good. Or -1's not looking good. When you're doing this, if you get to this point, you just don't need to keep going because there's no way we're going to end up with a 0 back over here, which is what we want, right? Okay, so the next simplest one to try would be, let's try 1/2. We can try +1. If we try +1, we get, so all right, I'm going to be hopeful. I'm going to try +1 because it's not too hard. Okay, so let's try +1. Bring down the 12. Well, this isn't going to work either. Okay, so 1 is not a root. All right. So get rid of both of those. Let's try the next one in line. Let's try 1/2. I'm using a little blackboard magic here and just erasing the things I know or I don't need and keep the things I have. Okay, so 1/2. Bring down the 12. 1/2 of 12 is 6. It's going to give me -14. 1/2 of -14 is -7. That will give me 12. 1/2 of 12 is 6. Oh, I'm liking this. -6 plus 6 is 0. Oh, I'm liking this a lot. 1/2 of -2 is -1. So 1/2, +1/2 is a root. Or a 0. So let's think about what my factored form would be. Hold on a sec, I have to give myself another blank slide here. I want to keep my annotations. May need a couple. What? Okay. Put my slides in the wrong spot. All right, now let's do this again. Okay, so I have found 1, 0. I have found that +1/2 is a 0. That means that x minus 1/2 is a factor. So what I've got here is x minus, my polynomial can now be written as x minus 1/2 times 12x to the 4th minus 14x to the 3rd, 12x to the 4th minus 14x to the 3rd, plus 12x squared minus 2. Okay. If we look at this guy again, so let's talk about a couple of things. We know we have not found, wait, positive, negative, positive. Okay, so we know we found neither the largest nor the smallest root because our signs on our lowest, on our bottom line here are neither alternating nor all the same. So there's a chance 1/2 is a repeated root. So let's try 1/2 again. It's not that hard to do. We'll just do it right here. 1/2, so bring down the 12. 1/2 of 12 is 6. Minus 8. 1/2 of -8 is -4. Positive 8. 1/2 of 8 is 4. Add those together. 1/2 of 4 is 2. And sure enough, 1/2 was a repeated root. So now what I have is x minus 1/2 squared times 12x to the third minus 8x squared minus 8x, plus 8x plus 4. Okay. Let's factor the 4 out of here. So we've got 4 times x minus 1/2 squared times 3x to the third minus 2x squared plus 2x plus 1. So my only remaining possible roots here now, if we do the p over q thing again, are positive and -1 and positive and -1/3. We've already eliminated both 1 and -1, so the only things we have left to try are 1/3. Let's go back here for a minute. Pause. Okay, so remember what we said about our numbers of positive roots. We've got 0, 2, or 4 of them. We still have not found the largest root. So let's try this again. So did I screw something up here? No. Okay. Let's try 1/3. So we're going to take 1/3 and divide that into 3, -2, 2, and 1. Drop down the 3. 1/3 times 3 is 1. 1/3 times -1 is -1/3. So this is 6/3 minus 2/3. 6/3 minus 1/3 is -5/3. Nope, 1/3 is not a root. So let's try -1/3. Little blackboard magic. Okay. Now let's see what we get. -1/3 times 3 is -1. Well, this is looking more promising. -1/3 times -3 is 1. -1/3 times 3 is -1, and we do indeed get a 0. So -1/3 is a root. So that means my polynomial, my f of x, is now 4 times x minus 1/2 squared times, x minus -1/3 or x plus 1/3 times 3x squared minus 3x plus 3. Let's factor out the 3 here, and we'll get 12 times x minus 1/2 squared times x plus 1/3 times x squared minus x plus 1 This guy will not factor, so let's use the quadratic formula. X equals negative b, which will be the negative of -1 plus or minus the square root of b squared minus 4 times a times c all over 2a. Sorry, a is 1. So this is 1 plus or minus the square root of -7 all over 2. So, whoops, not -7, sorry. -3. Or, so this is going to be 1/2 plus or minus square root of 3 over 2 times I. All right, so we've got our zeros. Let's write out what our zeros are. We've got a 0 of 1/2 with multiplicity of 2, a 0 of -1/3 with multiplicity of 1, and a 0 that is 1 plus square root of 3 over 2i, and a 0 that is 1 minus the square root of 3 over 2i. That's 1, 2, 3, 4, 5 roots. We've got a 5th degree polynomial. So our function that started out as (12x to the 5th minus 20x to the 4th plus 19x to the 3rd minus 6x squared minus 2x plus 1 can be written in factored form as 12 times x minus 1/2 squared times x plus 1/3 times x minus 1 plus the square root of 3 over 2i times x minus 1 minus the square root of 3 over 2i. Okay? All right, we'll do more of these in class. Conjugate pairs theorem. I've already said this, but let's look at it in math speak. If f is a polynomial function with real number coefficients and z is a 0 of f, then so is the conjugate of z. Real numbers, well, roots always come in conjugate pairs. This is kind of irrelevant for real roots because we only change the signs on the imaginary part, but when we're talking about complex roots that have got a non-zero imaginary part, if we know one complex root, we automatically know the other. So for example, let's look at f of x equals x to the 4th plus 64. We can factor this thing, sort of. Well, we can solve this thing, right? We can solve this algebraically now that we can handle square roots of negative numbers. And we can determine that 2 plus 2i is a 0. But let's just follow instructions here. And we've been given 2 plus 2i as a complex 0. Let's find the rest of them. All right, so we are working with f of x equals x to the 4th plus 64. We're told that 2 plus 2i is a 0. Let's use synthetic division to find a different one. And you maybe think, what? 2 plus 2i is a number. That means we can do synthetic division with it. We've got 1x to the 4th, 0x to the 3rd, plus 0x squared, plus 0x plus 64. Bring down the 1. 2 plus 2i times 1 is just 2 plus 2i. Add that together. 2 plus 2i times 2 plus 2i. That's going to be a little tricky, but use your scratch paper and do the multiplication. Actually, let's do that. Let's take 2 plus 2i and multiply by 2 plus 2i. 2 times 2 is 4. 2 times 2i is plus 4i. 2i times 2i is plus 4i. And 2i times 2i is going to be plus 4 times I squared. Okay, so what this comes down to is 4 plus 8i minus 4, which is just 8i. Add those together, we get 8i. Multiply through this, and we get negative 16 plus 16i. Add it down. And if you do the 2 plus 2i times negative 16 plus 16i, you get negative 64. And sure enough, 2 plus 2i is 0. Now, I could write out the polynomial that goes with this, but I don't want to. But our task is to find the rest of the complex zeros. All right, well, we've got this down to a cubic already. If we can just get it to a quadratic, then we should be able to do this. We know 2 plus 2i is a 0. That means that 2 minus 2i is also a 0. So let's go ahead and do this synthetic division. Bring down the 1. 2 minus 2i times 1 is 2 minus 2i. 2 plus 2i plus 2 minus 2i is just 4. So this is going to be 8 minus 8i, which is just going to be 8. Multiply 2 minus 2i times 8, and we get 16 minus 6i. 16i. Sorry, add those together, we get 0. So that means that f of x, which was x to the 4th plus 64, is actually can be written as x minus 2 plus 2i times x minus 2 minus 2i times x squared plus 4x plus 8. Hey, this guy will factor, and our polynomial can be written as x. Will that guy factor? No, he won't factor, but you know what? We can use the quadratic formula to find those zeros. So let's do that. Let's use the quadratic formula. X will equal negative 4 plus or minus the square root of 16 minus 32 all over 2, which is negative 4 plus or minus, here we go, 16 minus 32 is negative 16 over 2. So that's negative 4 plus or minus 4i all over 2. My other two zeros are 2 plus or minus 2i. So complex zeros can also be repeated. And my polynomial can be written as x minus 2 plus 2i squared. We got to erase some stuff. Times x plus, nope, sorry, that's wrong. Times x minus 2 minus 2i squared. If we actually put those back together, if we square these all together, we find out that our final factored form can also be written as x squared minus 4x plus 8 times x squared plus 4x plus 8. So our zeros are 2 plus 2i and 2 minus 2i. They both have multiplicity 2. And either one of these two work as our final factored form. Okay, one last example. We are going to use some information to construct a polynomial. We want to find a polynomial that touches the x-axis at the point 1/3, 0, has a 0 of 3i, and goes up to positive infinity on the right-hand side and down to negative infinity on the left-hand side. So what we're looking at is something like this. It's going to have a 0 here. Now it says touches. We're going to infer that means does not cross. So we want it to come up. It's going to touch. And that means it's going to have to go back down like that. So we're going to have another 0 right there. We can do this. And here's why we can do this. If it touches, so lowest possible degree, let's talk about that first. We've got 1, 2 real roots, and 1, which means 2 imaginary roots. Here's what we know. We know this thing touches but does not cross at 1/3. So we know we've got one factor, that is x minus 1/3 squared, because we want the lowest possible degree, but that thing's got to be at least of even multiplicity, which means squared. We've got a root of 3i, so we know we've got an x minus 3i. But if we've got positive 3i, that means we've also got negative 3i. And we know we've got one more real root. We're going to call that guy b. So this will be our polynomial. We get to construct this thing. So we can pick this number to be anything we want. We can find a polynomial. It doesn't say find the polynomial. Let's make this be -1. Or we could make it be 0. That would be another option. We could make it be there. We can pick any number we want. We could even make it be really anything smaller than 1/3. So we could make it be 1/4. Okay? But my choice is going to be x plus 1 times x minus 1/3 squared times, we could leave this as x minus 3i times x plus 3i, or we can put it in x squared plus 9. 1, 2, 3, 4, 5, fifth degree polynomial, If we graphed it, we would see that it satisfies all of our requirements. There's more than one answer here. There's actually an infinite number of answers. The things you don't get to choose, that 0 is set for you, as is its exponent of 2. These two factors are set for you, as are their exponents of 1, because we want the lowest possible degree. The fact that it goes up to positive infinity on one end and down to negative infinity on the other end sets us at an odd degree, so we have to have a 5th degree polynomial, which is how we knew we had to have one more root. So we have to have this front factor, but you get to pick that number. It can be any number you want. Okay, that's it for today. I will talk to you all again soon. Have a great day and do good math.